honor session, I guess you might call it. The people who won the award granted last night at the vote will be telling us in more detail about their poster presentations. So I have the pleasure to call upon Jean-Paul Biberian from Grenoble to tell us more about excess heat from solid-state electrolytes. Jean-Paul?
We're using a vacuum chamber. The original chamber was made of stainless steel. Later we changed it to quartz. The reason being that at high temperature, stainless steel is transparent to hydrogen, and we're leaking hydrogen. So we looked for leaks for years, and then realized it was true stainless steel itself. So we changed it to quartz. So some of my data are with stainless steel, and some are with quartz. So this is just a vacuum chamber, standard conflict flange. And we have inside, we pump it out with a mechanical pump, so in the 10-2 range only. And we have here a furnace. The furnace is about 10 centimeter long. And we position inside the furnace our crystals. So our samples are actually made either of single crystals or of ceramics. I won't go too much in detail of why we've done that. This is following suggestion, an idea, a patent of Francis Forat from the French Atomic Energy Commission. He's now retired. And he filed a patent in 1989 about the idea of making cold fusion with proton conductors. The idea being that if you can create vacancies in the lattice, you can fill them up with hydrogen or proton or deuterium. So we are fighting and struggling and trying to make these ceramics or these single crystals with lanthanum vacancies. Why lanthanum? Lanthanum has a valency of 3, aluminum has a valency of 3. It will change. If you take cerium, for instance, it goes from 3 to 4. Whereas lanthanum will always be 3. So you can make a material with vacancies, lanthanum vacancies, you can fill it eventually with 3 hydrogen or 3 proton, 3 deuterium. And if you apply voltage to that system, you might go even higher concentration in every one of these vacancies. So we started with the single crystals. The program started a few years ago with single crystals that were manufactured in the 60s to make lasers, solid-state lasers. At that time, they didn't want any vacancies, but in the manufacturing of these single crystals, they ended up having colored crystals. So you start with aluminum oxide, which is white, lanthanum oxide, which is white, and you end up with something that's pink or red. And in fact, the color comes from the vacancies themselves. Color centers. So we used those crystals for a while and got results that I reported at a conference in Monte Carlo. And since then, I mean, we used up all our good crystals, and we ran out of crystals. We tried to make some new ones last year, growing single crystals, but we failed. They didn't show any excess heat. So we manufactured ceramics. And instead of using the oxide as a material to start with, we started with nitrates. And apparently those ceramics works somehow better. Better than nothing. Not better than the other. The old good days are always better. So the single crystals are better. But we don't have to always like it. It's just like the palladium. So we mount, so those crystals are red when you start, but when you load it with deuterium, they turn white. That's easy to do experiment, it's reversible, you keep them in air, they go back to red. So here they are, we used 2 of them, and to have a good contact, on top of this sample, we deposit platinum or palladium. So recently we tried platinum. We're not sure if there's an influence or not of this deposit. If platinum is important, palladium can do the same thing, we're not sure. We tried for blocking interface. So platinum might hopefully block the deuterium from getting out of the crystal. So we use platinum in this experiment I'm going to talk to you about. And instead of using 2, one sample we put 2 so that mounting it is somehow easier. So we have a cathode in the middle, which is actually palladium foil, and 2 crystals around and squeezed by 2 other anodes. It's symmetric. So the whole thing is placed inside the tube, and we heat up at high temperature. Now, to tell you a few things about temperature measurements, there's an error here. It's not a thermistor here. We tried putting a PT100 resistor, platinum resistor for measuring temperature, but it melted completely. So it disappeared. So we use thermocouple for calibration, and then we use the resistivity of the heater itself, of the furnace itself, to reduce the temperature. So we regulate the input power of the furnace and measuring the resistivity will reduce the temperature by calibration. So the data I will show you are with this kind of measurements. Why do we have to do that? One major problem we have with thermocouples that when you go to high temperature in the hydrogen atmosphere, for some reason they don't work. I think the work function of these hydrides are not the same as the metals themselves. So at high temperature, all of a sudden you see the temperature going down, goes so down that it becomes negative at one point. So it's not zero that we reach absolute zero, it's that the thermocouple has changed orientation. So really good discovery. So we use the resistivity of the furnace to measure temperatures. So what we do basically is the following. We have, this is every square, every line horizontal in the x-axis is 1 hour. So the vertical scale is 1 degree centigrade. So I want you to admire the precision of our measurement. Because we're measuring 300 of degree at 500 degrees, so it's an achievement by itself. Now, what we do, we put, in that case, 100 watts in the furnace, and we're capable of measuring 100 micro. I'm trying to beat Professor Fleischmann, he was talking about microwatts, so we're doing the same. Now, so at that point, we turn a DC current through the crystal. In that case, it was 900 volts, continuous DC current. And the temperature rises very quickly. This is just Joule heating. Now, what we notice is that this is very fast. It takes about 10 minutes. The time constant of the system is about 10 minutes. And then there's a slow increase. Now, after, I don't know how many hours, 1, 2, 3, 4, 5, 6, 7 hours, we turn it off, and then the temperature decrease. That's fast, same time constant. And then a slow decrease, about 2 hours. Professor Lee is very interested by this time constant. Always ask me, that's heat after death. So we have 2 hours of heat after death. It's not as much as we could hope, but that's already 2 hours. So when we see that, we thought maybe we don't need to have the DC power. Since we have some heat after death, we can pulse the current. So we went into the pulsing mode. It's not AC mode, it's pulsing. That is, we are putting these 900 volts for 1 second every minute. So we divide by 60 the energy input. So now the energy input is about 2 milliwatts. And when we start putting the power in, actually it's before even the lines start going up. We started maybe 1 hour before. This is 6 hours per square here. It's not the same scale. This just to make things more confusing. To see if you're sleeping or listening. Because I see that a question. People ask questions, they didn't listen to them. Anyway, so we start putting the power in, pulse, 100 volt pulse, about 2 milliwatts, and temperature goes up. This is a glitch of the computer. We stop and have a problem, that's all. Then turn it off and goes down. Now what you see here, this shift, is due to the fact that there's a leak. This was a stainless steel tube, and at 550 degrees there's a small leak, so that the calibration is get slightly offsetting with time. So we repeated that. I don't have the data here because I want to pay $2 for a transparency made. But if you want to pay, I can take it. We did the same thing with 120 seconds, and we got exactly the same results. So we're putting about nothing in the system and getting something like 50 milliwatts of excess heat. So we're happy with the rate, not with the amplitude. Yes, I'm 5 minutes. Good. I don't have time for the joke. So we decided to go to higher temperatures, and we did the same thing at 620 degrees. And you can notice at this temperature the leak is even bigger because the slope is sharper, steeper. Now what we did here, we put pulses, same thing, pulses, but now the temperature instead of going up, went down. And after, this is 6 hours again. So after almost 24 hours, next morning, turn it back off and went up. So I said, well, the thing is screwed up, couldn't work. Let's try DC, see if the system reacts at this temperature. So we put the DC power, we put DC pulses. So forget about glitches here, they're just the computer fade. So at the same temperature, now we put DC voltage. In that case, 400 volts, 90 microamps. And now you see first an increase in temperature due to the Joule heating. So that means the system is responding correctly. When we put heat, it produces, temperature rises. So that's correct. And then it went down, stayed down, until you turn it off. And now we get exact opposite effect, went down and up again. So that's very troublesome. We have no idea what it does. I think it cannot be chemical because the energy involved are too large. I'm not completely sure about that, but I have this feeling it's not chemical because that would involve changing all the atoms of the crystals, basically. I doubt we can do it. It's not either loading. I thought that the first bit was just loading of hydrogen, an endothermic reaction of loading of hydrogen or deuterium with the lattice. Could have been that, it's way too much in energy. So I just don't know what it is. But I'm not a theoretician, so I just before finishing, because my time is limited, just can tell you the story. Because I like to say that I really enjoy working in this field. And I would like, I didn't think in my life when I was younger that one day I could work on something as exciting as cold fusion is. I think everybody here is very lucky to work in this field. I would like to thank Professor Fleischmann and Professor Pauls for having taken the risk of crossing the line, and so that everybody else can go now across the line. Maybe some people are running faster than the first ones, but it's really enjoyable. And to conclude, because I feel like I'm in paradise here, I'd like to tell you a story. This guy dies and he goes to heaven. And this guy would like to gamble, and he liked women. So he ended up in this place. It was wonderful, All the women were after him, and he was gambling and winning all the time. So after a while, women are good if they don't run after you, you run after them. So, and gambling is good if you lose sometimes. But he was winning all the time. It was no fun. So he said, oh, I'm tired of heaven. So he went to the door and said, well, I want to go to hell, and I'm tired of heaven. He said, this is hell. Thank you.
Thank you, Grandpa. That's a humor of your jokes. a question.
Okay.
You measure temperature by following the resistance of the heater, right?
Yes.
In my experience, the temperature of the heater or constant wattage is a function of the environment of the deuterium or hydrogen atmosphere. Is it possible that in the situation where the temperature went down that you were really having better heat conductivity from the heater and therefore having a lower temperature of the heater?
I didn't mention that because I didn't make a transparency for it, but I can explain it. In order to get this high stability, we had to put everything in the thermostatic box at 90 degrees. That made the system extremely stable. The outside temperature was constant. The heat flux was constant. And we had all the electronics stabilized. So we're pretty sure everything is correct. And the proof is that when we put this DC current, we really see first a temperature rise. The temperature rise indicates that the system is responding correctly. And the rise we obtain corresponds to exact joules we are putting in the system. So I think it's not...
But there's no change in the gas pressure then?
No, I mean, this is very, very low. You're talking about 1/10 of a degree at 600 degrees, so very low.
Please.
Jean-Paul, what was the atmosphere, how much pressure did you have in the environment, and what kind of power multiples were you getting?
Okay, we had a pressure of about 1 atmosphere, but that was at room temperature. So when you pump the temperature up, you kind of double the pressure. It's a 2 atmosphere range. We've done experiment with pure deuterium. We've done experiment with argon and deuterium, about 10% deuterium in the argon, to make sure nothing changed too much in the system. And the yield you're observing, if you look at the pulse mode, we're talking about 2 milliwatts, and we're getting 50 milliwatts. So we think we have about a factor of 25. But maybe it's more than that. We didn't try pulsing it less, because our time constant is 2 hours for the heat after death. So we could pulse maybe every hour, so that you're about infinity.
Thank you.
Next question.
Related to the pressure question, do you have any means of measuring loading? You mentioned color change. Can you calibrate color change?
You touch a really tough question. We tried measuring the weight increase, couldn't get any significant numbers. Theory, if we had 5% vacancy that we expect, we should see something in the weight. We didn't see anything. So we believe we're much less. We might try pressure changes. That should be visible. But we've not done it yet. That would be one of the things to do. It's not that easy to measure the amount of hydrogen in the system. We might try it.
Well, we better move on. Thank you so much, Jean-Paul. Okay, the next speaker is Elsie Case, who will address us on the catalytic fusion of deuterium. Dr. Case.
Well, as I mentioned before, I'm an engineer, not a physicist. I'm certainly not competent to deal with the kind of highly elaborate, detailed physical investigations that are reported here. What I am interested in is scale up. I want to build big power plants, lots of them. And of course, in order to build big power plants people will pay for, they of course have to be reliable. I got into this field when I noticed some work that looked very interesting and possibly scalable to larger size. And actually worked with Dr. Yamaguchi as a paper back in about 91, 92. And I was so intrigued I took it on myself to visit him in Tokyo. And I looked at this equipment and I saw this palladium disc that he had alloyed and deformed, and I said, this is very real. I think I'll get into this. So I did. Now, I'm a chemical engineer, and I had been fairly well acquainted with everybody who's working with palladium and to some extent platinum. And as a chemical engineer, I know what they are. They're catalysts. They're widely used as catalysts in the chemical industry and in oil refining and so forth. So I always felt that this is probably some sort of catalytic phenomenon. Now, however, I couldn't explain the nuclear reaction based on catalysis. I think I have a better idea of that after this week, but I thought originally that it was probably neutron co-catalysis. You know, deuterium is very susceptible to being bumped into and speeded up by ambient neutrons. So I thought that once you started to develop some neutrons, they would bump into some deuterium and make some more neutrons and so forth, and away we would go. So I originally started out my work, 6, 7 years ago, by looking for a laboratory that was equipped to handle neutrons, to generate neutrons and to measure neutrons. And I rapidly found out that I couldn't afford anything or get an agreement from anybody in the U.S., so I went to Eastern Europe. And to make a long story short, I walked into a nuclear laboratory center in Prague at the Charles University, and the director was sitting right there, and I told him what I wanted to do, and he said, "We'll do it." I said, "Who has to approve it?" And he says, "We'll do it." So we did do it, and it was very inexpensive. And it's a nice little laboratory. It's not highly instrumented, but they know what they're doing. And I went to Prague about 6 or 7 times, trying to use neutrons to get this catalysis to go, and once it was going, to measure the neutrons that were being developed. And at some point, I finally got, what I had been doing was always getting more and more close to catalysis. And I had made my own catalyst for a while and done things like plating my own catalyst out on metal tubes and so forth. I finally got into simply scanning through commercial catalysts, or ones which I could buy or get samples of. Finally got one of those that gave us a 1.9 centigrade temperature rise, which was astounding to the physicists there. And he asked me, "Hey, how did you choose it?" And I said, "It works. This is the one that works." But finally, we got to the point that I was getting discouraged about the neutrons, and it turns out Prague has a very, very noisy electrical system, and we simply could not measure the neutrons to the appropriate sensitivity during the week. And I finally got a Russian graduate student to stay with me on Saturday. And finally, on Saturday afternoon, all the other machines in town had shut down. And we had a window of about 30 minutes in which their neutron scaler was operating versus a real lab count. And there were no neutrons at all. None. And that pretty well killed that. It obviously wasn't neutron generating nor neutron, and incidentally, we were operating with a temperature rise at that point. So I stopped my trips to Prague and set up in my own basement and tried to set up some equipment that would allow me to scan through lots and lots and lots of potential catalysts that might do the job and conditions that might operate to cause fusion of deuterium. Well, it took a while, and I had quite literally dozens and dozens and maybe a couple hundred of negative results, but once in a while I was getting a positive result. And I developed a little some bench equipment, which I was pictured at my poster session today. Don't have any view graphs. And a procedure for checking out the catalysts. And I really ought to tell you what this process is, because it tells you what I corrected for and what I may or may not have corrected for. What I did was to develop this process of, it was a little reactor in which I put some catalyst, and then I would put hydrogen into it, heat it up, and incidentally, every single one involved a blank with hydrogen. and then a real run with Deuterium. It wasn't one blank and then a whole bunch of runs with Deuterium. It was always one blank followed sequentially by a run with Deuterium. Anyway, I would heat it up, and finally found that it had to be heated to at least about 150 centigrade to get anything to happen. Later, I found out that if I went much over 250, it died. The catalyst was killed. And I found out very much later that the reason for that is that the catalyst become centered. Platinum and palladium, believe it or not, center at 250 centigrade, which is not much higher, but they center at 250. Anyway, so the typical run that I finally zeroed in on is I would heat the hydrogen up to about 175 centigrade, wait until after an hour or two, and the temperature would go up and then level out, form some sort of asymptote. And then I would vent it, and frequently I would get a little bit of steam condensation in the vent, indicating that there had been some reduction of an oxide on the catalyst. So I'd have to evacuate with a vacuum pump, put in some more hydrogen, do this all over again. And I would do this sequentially with hydrogen until the asymptotes were within a half a degree or 1 degree or so of one another sequentially. At that point, I then felt comfortable that I knew what the baseline was for that particular catalyst. And I could then, on my next go-round, evacuate and load the deuterium, put in the same power, and see what the temperature would then result. Now, if it was about the same, degree or two higher, or sometimes lower, that was no result. Only if the temperature with the deuterium was at least 5 centigrade higher than with hydrogen would I call it a positive result. And the positive results were few and far between initially. But I finally found a set of catalysts that are all a type of family out of this huge, vast potential supply of commercial catalysts that are known to be active in hydrogenation that would work. And I got temperature rises then of deuterium over hydrogen of at least 5 centigrade, usually 7 or 9, and sometimes as high as over 20. And the catalysts which were active turned out to be, they were all platinum group metals, they were all on active carbon, they were all at about 0.5% to 1% metal loading on the carbon, and they were all off-the-shelf samples from manufacturers, and there are several manufacturers that produce such materials. Now, as a matter of fact, there are probably, I guess, 2 or 3 manufacturers produce 3 or 4 or 5 or 10 candidates within this range and offer them for sale. Now, they don't always have everything for sale, but they're in the catalogs. And the manufacturers, for your information, one of them is PMC, which was in Seaverville, Tennessee. They have given me several samples that work. One that I worked also with is United Catalyst in Louisville, Kentucky. And I think there are also some candidate catalysts that can be obtained from Johnson Matthey, from Alpha, which is I think a branch of Johnson Matthey, and so on. But also, it isn't only palladium. Palladium works, platinum works about as well. And rhodium works, and iridium works. I don't know about ruthenium. Now, in the product, I had the gases, I had the off-gas analyzed several times by the giant magnetic sector mass spec at Oak Ridge. And twice, once in quadruplicate and once in triplicate with a non-result. Found approximately 90 to 100 parts per million of helium-4. There was, of course, air, water in the mass spec, oxygen, a little bit of oxygen, hydrogen left over from where it wasn't completely removed in the first place, and so forth. There was no methane. noted. And of course, if one thinks, and somebody has suggested maybe it was a hydrogenation carbon emitting methane, there would have been a lot of methane in the mass spectrum that wasn't visible. Well, okay, I've got the catalyst. I don't have a system that can be scaled up very well. I'm working now on a couple of demos. In fact, I hope to make a demonstration late next week. And a couple of the attendees here have volunteered to try to reproduce the results in their equipment. And, well, I hope and I think they may well do so. Now, what I have proposed here then is a narrowly defined catalyst that does work apparently to fuse deuterium into helium-4. Now, that is a solution. It may not be the best solution, probably isn't the only solution. But it is a solution, and it is on off-the-shelf metal. So, I would hope that, as I say, some people will reproduce, and I would hope that some people would take some samples of these catalysts, which will cost me maybe 3 samples. You put them into your analyses and see what it is that is special about these metals that might account for why they're active. It might give you some sort of clue about what you would do in your own work. Again, a lot of people are spending a lot of time to make some very elaborate platinum, palladium, coated crystals and so forth. And this may be a lot easier and cheaper way. And also, of course, these things are pre-screened. The companies aren't going to offer you a hydrogenation catalyst that doesn't work. They've got years and years and years of experience. And it just so happens that these particular hydrogenation catalysts appear to work for fusion. So you don't have to check it out. It better work. Now, of course, if you get outside the parameters, one other thing. 150 centigrade is required in my work to get some results. And at about 250 and higher, the metal centers. At least the palladium does. I think platinum also does. Rhodium, I forgot. Anyway, despite the fact that these metals are very high melting, they center at 250. So there's this narrow range of 150 to 250, and this narrow range of catalyst compositions. The pressures somewhere above atmospheric, and I don't think those affect the pressure. Well, it's a work in progress. I've been making a demo, and a demo big enough to get somebody interested in making a power plant, but we'll see. Thank you for your attention.
Question, did you see any helium in your regular light hydrogen case?
I never analyzed the light hydrogen. And as a matter of fact, I do not know for a fact that there was nothing happening with the light hydrogen. What I do know is that I got an apparently significantly greater reaction with the deuterium. So I was just blanking out what I thought to be the chemical reactions and looking only at the things that were non-chemical in nature. And you can quibble about it, I guess, but this was the way I was directed.
Yes, and question. What's the volume of the chamber?
1.6 liters.
And what's the pressure change when you put hydrogen or deuterium in it?
Well, I generally operated at 40, 50 psi.
But it drops or it doesn't drop? I mean, the absorption?
Because the temperature rises so much, the pressure would frequently rise to 60 to 70 psi at operating conditions. But again, as I say, I tried a couple of times to see if there was any pressure effect, and the pressure does not seem to affect the reaction rate much within the pressures at which I tested. But temperature made a big effect.
Did you use just the pure powders or the powders on these large supported spheres or?
No. What it is a prepared, commercially available hydrogenation catalyst, which is 0.5% to 1% coated on activated carbon chunks. So these were little chips, approximately a centimeter across, that by a proprietary process, which they didn't tell me what it was, they precipitated the platinum and palladium onto it and then reduced it and then sent it to me. Yeah. So I have not fully characterized any of these catalysts. All I know that you can order it by a particular code number from a particular manufacturer. And since they all work, I'm not terribly worried about finding out what they individually are, but I would hope somebody would be worried about it.
Now, most of these things are actually put on very fine carbon, and the carbon's diffused into either alumina or zirconia to get it.
No, these are precipitated on activated carbon chunks from, most generally from coconut shell activated carbon. And it's precipitated directly from the solution onto these chunks and then reduced in situ and then sold in that fashion. But there are a lot of fine details about how you do this because the activity does depend to some extent on how they precipitate it.
Okay, thanks.
Scott?
What was the excess power that you would typically get out of the?
Well, I calculated it about 5 to 10 watts.
5 to 10.
It was approximately 10% of power input, but it wasn't very well insulated. I didn't use a door or anything of the sort. If I used much better insulation, I could estimate easily, even on this scale, that I'd be doing upwards at least 50% excess power. And then I did try to optimize the power output. And I got certain samples that were better than the commercially available ones. Oh, incidentally, I will give to any of you the description of the code numbers to ask for the samples. And if you want to really optimize stuff, I got to get a bunch of us together and then we'll order some.
Okay, thank you very much. Next is Dr. Francesca Celani from Kasagi, who will inform us some more about the Cincinnati experiment.
Okay. So this again results about the finished results with the Cincinnati. We run Excitation is a specialized, I want to stress this point, nuclear laboratory based in Italy with people with very long experience and very careful. This experiment is not a toy, so only relative can do. I do not myself, I just watch them. This laboratory has very long experience managing plutonium, uranium, and thorium. Thorium has the characteristic to be absorbed from zirconium, so it's very difficult to take off completely. So only people with very long experience can avoid fast results due to this characteristic of thorium. A sketch of this cell is a zirconia cylinder with at the center a zirconia disc, where is applied some AC voltage from maybe 10 volts to 220 and current as large as 8 amperes. The temperature of the system can increase abruptly to 200 Celsius. The pressure can increase abruptly because there is a positive feedback between the electrolyte conducibility and the current applied, the voltage applied. So the temperature increase, the conducibility increase, so the pressure increase, and so on. According to Cincinnati procedure, we used 25 milliliters. The solution is about 1/3 of the volume of the full cell. We made in total 4 experiments, 2 experiments blank to be confident with this kind of device, and 2 black to check about thorium transmutation, if any. So the cell before operation was strongly acid lineate and acetone and so on, and to be more sure, because the property of thorium to be attached to the surface, mechanically polishing 100 micron. So we ran the first experiment, and we just changed, instead of thorium, we use sodium nitrate, and try to follow as much as possible the Cincinnati protocol, but using the acidity we have in Italy. So it means 50 years instead of 60. And maybe this can be the reason why the pressure increased in a very short time, and we cannot control it, and the safety valve luckily broken. So the second experiment, we decide don't use sodium nitrate, but just the hydrochloric acid, because of the calculation about the pH, not so important, this amount is respect to hydrochloric acid. And we modify a little bit the protocol. So instead to work at constant voltage and current free, use the approach to start from low voltage, only the voltage beginning, and we control it. It's a way the amount of current, in the meaning that we increase voltage only when the current decreases. So this procedure was shown safely. So after this procedure, we clean completely the cell again with acid and mechanical polishing. The third was the black experiment, at least. So in the third experiment, we followed the protocol we have found safely and used thorium nitrate. In our condition, we don't have only natural thorium-232, but from the point of view of radioactivity, we have a big amount of thorium-230 coming from uranium decay. So the ratio between artificial thorium natural is 12 to 1. The total activity, if I well remember, about 440 becquerel. The experiment was run for about 1 hour, and to analyze the data, clean the cell, and be completely sure what happened in 1 hour experiment, we spent 1 month. The fourth experiment, second for the black, used a compromise between the Cincinnati protocol and our procedure. The results was similar to experiment number 3. In this case, we make a completely qualitative analysis of the material of the elements collected. At the bottom, we make radiometric analysis, total radiometric analysis, alpha plus beta. This experiment and this other. I want to stress some point about the results. We use an approach to cross-check the data between the ICP mass spectroscopy and ICP optica. Because if we use only ICP mass, we have a lot of new elements to match. We think are just a composition of molecular of several elements. So can be fake result. So after this strong strain, we checked and select some elements. This was the most relevant. So from the chemical point aspect, we lost, we've got to collect 80% of thorium initially. From the radiometric, 12%. For experiment number 4, just remember the same number, 22 chemical and about 14 radiometric. The quantity analysis of the elements detected was voluntary level natural, 3.2 milligram, kappa, 1.1 milligram, but the isotopic ratio was not natural. Cesium 133 and mercury. The other elements are in progress. one other important point, because we use strong action attack, we use only Teflon, never glass. This is the first experiment. At this time, at 20 minutes, the pressure temperature go too much and we have to stop because broken safety valves. Second blank can work safely. To 220 volts, we reach. So Cincinnati recommend 177, but we increase more to check what happened. So it means high voltage to low current. The black experiment in some way followed the experiment number 2, and we increased the time of the experiment. Instead of 55 minutes from Cincinnati, we increased more than 20% between the ratio between 60 and 50 Hz, and something more to be sure. So total 55 minutes experiment. And the current was not so large. At the beginning about 3 ampere, and after typically about half ampere. Number 4 was the compromise experiment about this procedure. So the temperature increased to 120 degrees. The pressure increased, but in a controllable way. At the current higher, peak about 5 ampere and typically 2 ampere. So, conclusion, I could just start with point. According to our results, it seems the coordinate Cincinnati cell is able to transmutate in some way, or even another name, we don't know, thorium, both natural and artificial. The amount of transmuted material is less, typically about 15%, respect to what claimed in other experiments from other people. But even if something happened. And we cross-check the result with the 2 techniques, and we stress is very, very important. And moreover, okay, to the study in the chance at the beginning, we started in February. A big caution, this is not a toy for people with no big experience. Never give to university students. We have these of high pressure, high temperature, high voltage, and radiation. So it's okay.
Sure, there are questions. Yes, please. Larry Forsley from JWK. A couple questions for you. One, are you sure that you haven't played out the inside with thorium?
Yes, we check if this is some thorium inside the cell, because we build a special alpha detector that check, that match very, very narrow the cell inside. Check if some thorium remains. Moreover, we scratch the surface mechanically, dissolve all the cell in chloric acid, and we analyze all the material collected with alpha conspecta total radiometric.
Okay, the second question I have for you. Have you considered to run as a blank, the same cell, same conditions?
It was the same cell.
I'm sorry?
It was, we have only one cell. So
Please, take the same cell, take the only cell you've got.
yes.
With the same conditions, just at a lower voltage, perhaps only 10 volts for the time period. Presumably there'll be no reaction, but it'll give you an opportunity to see if anything is happening in there.
It's blank cell is used to take confidence with the system. So maybe if you work a longer time, something can happen. I don't know, you work about 1 hour.
Okay, thank you.
Yes, many questions, but anyway, it's one thing. We received some samples from the Cincinnati group. We analyzed them by LCPMS. We've done 4 or 5 analyses actually, One of them was an active cell, but with sodium methyl silicate as the electrolyte. And we looked at the spectrum. In principle, what they did after the experiment, they took the electrode, the zirconium electrode, that etched it in nitric acid and chloric acid, and they gave us whatever it was. So we analyzed it with the ICP-MS. I can't tell you what we saw for copper and light elements because the print I have from the mass spec is not sensitive enough. I will know it very soon, but not right now. But what we have observed, accretion of tin, lead, but most surprising, thorium, and there was no thorium at the beginning, and uranium, including uranium-235. So that's my point. What can you say about uranium-235 unless it's coming from Russia? Zirconium is coming from Russia.
Okay. We have some indication, some early element that thorium was in our cell, but because the result is so strange, we want to make an experiment because it's really strange. So it can be, but we want to check it. So maybe you are right, but we want to check.
Yeah, one of the most interesting things in this conference is the idea that cold fusion or some form of cold fusion can reduce radioactivity. If this was true, it would be wonderful. But the experiments we've all heard describing, like Larry Forsley and yours, John Paul's, are all doing the experiments where there seem to be several elements. So I think perhaps the best way, instead of starting with uranium or thorium, which has many decay products and big problems, would the solution perhaps not be to take one single radioactive element? Because when you have a fission, you're worried about iodine, you're worried about sodium, so take one single element, for example, iodine, and then try and see whether you destroy the radioactivity of this single element. And that should be a clean, decisive experiment.
I agree with this aspect. Our next step, now we have some planning. Maybe we will start with cesium. Probably cesium, the intrinsic radioactivity is element. So the amount of chemical material is very low for safety reasons. So we have to find some compromise between the minimum amount of radioactive material and the sensitivity of chemical analysis and the safety. So we have to watch around to find some good candidate because the safety reasons are not so weak. So the beginning we could be so later we will attention.
Any other remarks? If not, thank you so much, Francesco. The next lecture is by Dr. John Fisher, who will tell us more about the role of polyneutrons in cold nuclear reactors.
I'd just like to say again that this is a theoretical presentation. I begin by accepting that there really are nuclear reactions of a new type that are taking place, and that they produce nuclear energy, and that they produce transmutation of the elements of a new kind. But I leave open the question as to just what these reactions may be. In particular, they may or may not be deuterium fusion. Reaction, yes. Nature, we don't know yet. Then I ask the question, can we understand this new class of nuclear reactions within the accepted principles of nuclear physics? And that's the question that I want to address now. Nuclear physics provides 4 ground rules for cold nuclear reactions that are capable of producing macroscopic quantities of energy. We got macroscopic quantities observed, and that's what we have to account for. Now these 4 ground rules are, first, all reactions must involve just 2 reactors. You try to have 3 reactants get together at the same place at the same time, that's just too improbable. Second, of these 2 reactants, one of them has to be neutral. Charged nuclei just can't react at low temperature at an appreciable rate. Third is that all the reactions have to be exothermic. And a fourth is there's got to be a chain reaction, because you need enormous numbers of neutral particles to generate macroscopic quantities of energy. So, the question is, what are the neutral particles? We know what they are in ordinary nuclear plants. They're neutrons. They go between uranium atoms, make a chain reaction. But they can't be neutrons in the stuff we're working with, because a lot of people look for neutrons and are too few of them. Well, it might be polyneutrons. Polyneutron is a little droplet of nuclear matter made entirely of neutrons, no protons, just neutrons. Those would be neutrons. Might be them. Or if not them, some exotic new particle, unknown to science. I don't see other possibilities. And in this work, I'm exploring the possibility that these neutral particles that we need are polyneutrons. Now, the possibility of polyneutrons is not new. This is from a review article published about 10 years ago. I lost the, here it is. These fellows say, look, here's the standard branch of the table of isotopes. Maybe there's another one down here where we've got isotopes that are either pure neutrons, down here with Z equal to 0, or some other things with very few protons, mostly neutrons. They call them neutron nuclei. I'm calling these things down here polyneutrons. That would be nice. And people have tried actually to calculate, you know, how big a bunch of neutrons do you have to get together before it will find into a little droplet. And the mental picture they have is, look, we know if we're working with helium, we take 2 helium atoms, they won't stick together. Take 3, they won't stick together. You take a big enough bunch of helium atoms, they will stick together. They make a drop of liquid helium. And the physicists expect the same thing to happen with neutrons. They know that 2 don't stick together. They know that 3 don't stick together. But maybe if you get enough, when you get enough, they will stick together. And make a little drop of liquid neutron. They polyneutrons. And they tried to calculate from first principles what's the smallest droplet of neutron that would hang together. And nuclear physics at its present stage is not good enough to do that. They have trouble trying to calculate what the smallest one is. And various people have got various answers. And I certainly am not capable of doing it from first principles. So I tried to develop a quantitative treatment of polyneutrons by making a liquid drop model for the mass excesses of polyneutrons and other extremely neutron-rich isotopes in this range here, both the Z equal to 0 and the Z equal 1, 2, 3, 4, down in this range. And since I couldn't do it by first principles, I had to do it by appealing to the experiments that you guys have done, to try to work backwards from experimental results to get the parameters of the liquid drop. And I didn't get it right. And I didn't have enough evidence to guide me. So I was stuck for several years. And I probably would have been stuck forever, except for the beautiful experiments of Miley and Associates, who's got me going again. here we have, you're familiar with this, but look, out here around 200, the production rate of isotopes of that mass and in that range are 100 or 1,000 times as great as in this gap in between. And then up 100 or 1,000 times as great with a gap. And up again and down with a gap. Up again. You've got those bands of very high production separated from each other. And this is not, they're not the only folks who did that. Nucleon-Loaded and his associates. It's lined up. In a different experiment, in a different continent. Got the same sort of results. You've got a bunch here, a bunch there, a bunch there, a bunch there, gaps in between. Now, first you might think that those are ordinary isotopes. For example, that this would be lead up in here and so on down. But then the thought struck me, you know, we're not sure of that. I know that Miley and Rizzo both measured here and there a few of these and found they were ordinary isotopes. But the thought I had was, well, suppose that the majority of those really belong to this new branch of the table of isotopes, down there hugging around zero charge. If that were the case, then I could use, then I would interpret this, you see, that these are stable isotopes. This is background. Any isotopes in this range that you ever made would be unstable, would decay, disappear. Here's a bunch of stable ones. Here's no stability. I got 4 regions of stability. From the bounds on that, upper and lower, I can deduce the parameters of the liquid drop model that I was trying to find. So I tried that. And I got this again is not from first principles. I'm just fitting my liquid drop parameters to their data. And I got a band of stability there, 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 there and there. Fits it pretty well. Well, that encouraged me a lot. I'm going to save this one for future reference. Now, just to clarify this is the regular branch of the table of isotopes. These are the stable elements in it. Of course, there are unstable ones on either side. This thing goes up above the ceiling there for lead and uranium. The second branch, extremely neutron rich, only goes up to about here. And you'll note, if I look over there, there's the nuclear charge, 6 protons. That stuff is carbon, carbon 200. And there are a bunch of isotopes there, about 20 different isotopes of carbon in that block. Those are the isotopes that Professor Oriani looked for and found evidence for. Not conclusive, but suggestive evidence for. Now, just to make things clearer here, I want to take a look at mass number of 66 and see what things look like. This is the ordinary branch of the table of isotopes, where zinc is the stable one. And you'll notice that there's a lot of scatter around how you would fit this with a liquid drop model. That's because of nuclear shell effects. You get nuclear shell effects because the isotopic spin changes from, as you go along here, from 0 for arsenic to 7 for iron. When you go up and look at this is the other branch, where beryllium is the stable one. There, the isotopic spin is 33. The isotopic spin doesn't change as you go changing the charge from a polyneutron through hydrogen, helium, lithium, beryllium, and so on. And because the isotopic spin doesn't change, the symmetry of the nucleus doesn't change, you don't get the jiggles due to shell model, and the liquid drop model works better for this second branch than it does for the first. Now remember that in those shaded blocks, those isotopes are stable. If there are any of them in nature, which I assume, but not very many of them, they've been around for geologic time. So they're available to be used in reactions. A neutron hitting, say, lithium-35 in one of those blocks, or carbon-208 in another one, will cause fission. And off pops a polyneutron and 18 lithium. Here pops a polyneutron and 185 carbon. These are exothermic reactions, and I can tell they're exothermic because my liquid drop model tells me the mass excess of lithium-35, of the polyneutron, of lithium-18, and the textbook tells me the mass excess of neutron, so I can see that that's exothermic. So you can make polyneutrons in an experiment, even though the polyneutron doesn't exist in nature. And they can, polyneutrons are very reactive. Here's some interesting ones. A polyneutron of any size interacting with lithium-7 picks up 2 neutrons, gives off helium and hydrogen. Then the 20 interacts with lithium, goes to 22, gives off helium, hydrogen. On and on. 1,000 interacts with lithium, 1,002 helium, hydrogen. This is where the helium comes from. When you've got lithium in the electrolyte. There's another class of reactions. In the cathode, a big polyneutron, take 1,000 for example, interacts with 58, with nickel 58, and the polyneutron fissions into a big piece and a little piece, 2 polyneutrons. Some of the neutrons are picked up by nickel. They're more tightly bound to nickel than they are in the polyneutron, which makes this exothermic. I got 2 where I had 1. Those 2 diffuse back into the electrolyte, and they grow. They diffuse back into the cathode, they split. There's a basis for a chain reaction. Now you wonder, can I, this is all nice, but can these reactions get back and generate those bands of isotopes that Miley and Hutano and their associates found? And the answer to that is yes. These are some more exothermic reactions. Take a big polyneutron, interact with hydrogen, makes hydrogen-24. Hydrogen-24 beta decays to helium-24, helium-24 beta decays to lithium-24. That's as far as it goes. It's now up in one of these blocks of stability. And that's the end of the line. So you made lithium-24. It can go the other way. You can get a little polyneutron and a giant hydrogen, hydrogen-977. Well, that starts beta decaying. And after a while it fissions, and finally it's done. And in that way, you can reproduce the data of Miley and Hutano. That's the end.
Yeah.
However,
Questions and comments? Yes, please, back there.
Let's see, could I see your transparency where you start chain reaction? The neutron is presumably coming from background, environmental background, and you start all the reactions. If that's the case, everyone should see it, not just Professor Oriani, George Miley, or everyone else. Everyone else who are doing some experiment should see same thing. How you explain that? And another thing is all this chain reaction, you sort of rearrange so that you get the final product conveniently to fit your skin. How do you know that process really takes place?
Very difficult with understanding the question. If I interpret the first one, it is that these groups of isotopes that Miley saw and a group of isotopes that Neutrino saw, other people should see if they look. I agree to that. They should see them if they look. But as far as I know, most people have not looked. And the second question, I did not get because this machine made more noise in my ears than the question, so I'm sorry about that.
The second question was that in the chain reaction you proposed, how do you know that reaction actually occurs? You seem to rearrange so that you conveniently you get what you want, rather than using some theoretical reasoning to say that's the way it's going to happen.
Once I get the liquid drop model, I'm stuck with its parameters, and I am stuck with the mass excess values for all the extremely neutron-rich nuclei. And then I can ask the question, what reactions are possible? In, for example, a system that involves palladium and lithium, which is one of a very interesting system. And there are some exothermic reactions. One of the exothermic reactions is the reaction that leads to the growth of a polyneutron by taking pairs of neutrons away from lithium-7 and leaving behind hydrogen and helium. Another reaction that is exothermic is this one that causes fission of a polyneutron into a big part and a little part, making a chain reaction possible. I was gratified to have the soul because it does account for the observation of helium coming from the electrolyte, which is what people observe, and it does account for building up a large number of neutral particles that you need for massive macroscopic energy release. But if the parameters of the liquid drop model that I got to fit Miley's data hadn't made that possible, I would have to conclude, well, then the model is wrong. What I have built here is a house of cards. You can take away, any cards you take away, the thing will fall down. This model, it either explains everything or it's wrong. And there are so many things where it can be checked. But I expected it was wrong to come tumbling down shortly.
Let's go on to the next question, Stanshot.
What is it about the electrolytic environment that would be conducive to producing the polyneutrons, or, you know, is there something special?
Why electrolysis seems to make this go better?
Yes.
The chain reaction that I indicated here involves polyneutrons doing part of the reacting in the electrolyte and part in the cathode, which means that these polyneutrons are very close to the electrolyte cathode interface. And the configuration of the cathode, whether it's got cracks in it, whether it's got surface layers in it, would affect that. And it seems strictly possible to me that the effects of electrolysis on the cathode, conditioning the surface, will affect the degree to which the chain reaction can be supported.
Any other comments? Or just the first one?
Excuse me. Did you've read the George Onderland's 4 abstracts at the beginning of our abstract book. He's talking about the dineutron and the other polymeric neutrons. Have you been in touch with him regarding his theory?
Not personally, no. But I have taken a careful look at dineutrons. That's one of the reasons I got the book by the two Russians. They summarized the work on dineutrons. And dineutrons are not bound. They're too small to be bound. They fail binding by about a tenth of an MeV. They have a transient lifetime, dineutron, but it's such a short lifetime that it hasn't got time the speed of light to get into a nucleus. So I set dineutrons aside. It has to be in there.
Okay.
John. The next talk is by Steve Hrushovetz, if I'm my pronunciation. Let me say that this man is a student in Winnipeg, and his poster got the second highest number of votes yesterday.
Hello, Nestor. Let me just say it's an honor and privilege to be given a chance to be able to speak to you again. As I showed yesterday, the title of my poster is, well, in your books, it's this long word title, Integer-linked elementary particle charges and the theoretical role of neutrino oscillations in nucleon-loaded metal anomalies. And I've shortened it for the poster and the manuscript for just particles, primes, and cold fusion. Various particles and interactions have been considered in explaining cold fusion anomalies in nucleon-loaded metals like palladium and nickel. My poster presents an original prime number approach to elementary particle charges and theorizes the role of enhanced neutrino decays in these cold fusion anomalies. To briefly give an overview of these elementary particles, they're quite well known in terms of what they are, but some of their properties like mass, it hasn't been entirely been refined to a very accurate amount yet, but basically you'll have these 12 elementary fermions can have particles, and the gauge and heavy bosons involved in field interactions, W and Z being involved in weak interactions, gluons being involved in strong force or color force, and there are actually 8 kinds of gluons, 6 types that have color and anti-charge and anti-color combinations. There's 3 colors and 3 anti-color charges. And the other kind has 3 color and 3 anti-colors. And there are 2 types of those. And these different fermions are distinguished by their electric charge, their color charge, and I'd like to point attention to 2 ones in particular. First of all, the up and down quarks, which are the quarks used to make up neutrons and protons. There's 2 ups and 1 down for a proton, and 2 downs and 1 up for a neutron. And also these neutrinos, which the electron neutrino, mu neutrino, and tau neutrino. There's not really a consensus on the mass of neutrinos, but there is the view that if you do have mass, they might explain some anomalies in astronomy like dark matter, and also things like a deficit in the expected neutrino output from the sun, the so-called solar neutrino deficit, and also a ratio of 2 kinds of neutrinos in atmospheric cosmic rays. My theory proposes that they do have mass, and I'm going to get to that right away. Basically, at least 2 of them do have mass anyway. My theory involves using 8 prime numbers in a pattern of using them 5 times, that set 5 times in 6 different groups. The groups are, in the table I'll show you, are in bold outlines, and they each have only 1 cofactor. And here are these 8 primes. 2, 3, 5, 11, 149, 863, 1831, and 178, 441. Okay. Sorry. Yeah, here we go. The ones in brackets are the ones that are used for each fermion family. There's 6 of those, and the 2 and 3 are often used for the color and electric charge ratios. The other couple of rules that I used were in setting up this pattern where additions and subtractions occur in the same charges and no prime is used as an exponent. Okay, so let's get to the table here. We have briefly the color charge group where, well, I'll get to the electric charge here. first. The unit electric charge is described by all 8 prime numbers in a certain arithmetic pattern with a plus and a minus. And for the unit color charge, I switch the plus and minus of that, so that even at unification energies, this will be slightly higher, the color charge. And then the 2s and 3s create those other electric charges. The 2 cofactors in each are encircled in blue. Now for the fermion mass numbers, I use the 6 primes, 1, 2, 3, 4, 5, 6, and a plus and minus in the down quark. This minus 149 would be important for the relation to cold fusion. And also there's the electron neutrino that is 0 mass in my area. The other side of that table that was in my poster goes like this. You have the 6 different primes. 149 is the muon neutrino number. 11 times 149 is the tau neutrino number. And there's 3 cofactors for fermion family 3, 1 for the fermion family 2. In the gauge and heavy boson masses, I start with Z as the sort of basic number, and then multiply that by other ones for the Z number. And different combinations, arithmetic combinations of the W set here create the other particles in that group, except the leptoquark, which is 5 times Z. I predict the mass of the Higgs particle based on switching these 2 numbers. And the 2 gluon masses I also assign as switching the W set, but dividing by Z in one case, and also just dividing them instead of multiplying by Z in that case as well. Now once you have that pattern, well, I should point out also that the reason that this might seem a little arbitrary to get some of these numbers is, first of all, one thing I should point out is the down quark and the strange quark have 2 denominators, 5 and 11. That was interesting to me and useful for figuring out why those are those masses, because there's a kaon called the there's kaons that are composed of downs and anti-strange quarks, and they have a long-lived version of them that has a CP violating decay, charge pairs violating decay, and they have 2 fractions, and one of the fractions of the CP violating decay seem to correspond to the mass, or the mass number even, divided by the Z mass number, and multiplying that number by 5 over 11, which is the 2 denominators, gives you the other CP violating fraction. So basically, this gives a better sort of overview of the sort of thing here. One thing I wanted to point out is the minus 41, 149 there, and 149 here, and 149 there. That'll be important for the cold fusion application. The other thing was also, this electric charge was related to the highest mass charge in this group by equating the gravitational force of those 2 particles and the electric force between particle with unit charge divided by that number. And in order to come close to the values of the constants and everything. So it makes sense in a second, basically. If you convert these numbers into masses, for instance, you get this set here. Basically, I won't go through it all, but basically, they seem to fit the patterns, the ranges and mass ratios that are given in tables that are known. And one thing I'd like to point out here is the 0.0882 MeVs. This is an MeV of C squared, which corresponds to 88.2 kilo electron volts. Before I get to the importance of that, I just wanted to point out here at the bottom the reason for the electric charge and the leptoquark charge, where if you equal electric gravity force and you have electric force is E divided by that number that I showed previously, and the gravitational force between the 2 leptoquarks, and you equate those 2, you get a GN of this number here, which is pretty close to the accepted GN value, and it might be used for determining that value, which is hard to find. It's actually outside what is the standard value, but recent experiments, as I referred to in my manuscript, have shown it within the percentages that you need to show. All that stuff basically helps to reinforce this pattern number, and applying it to cold fusion occurred to me when I read about, in the last conference that you had, 89 plus or minus 1 keV X-rays were observed by an Italian group, Cignini, Gozzi, and al., and in heat-producing cells loaded with deuterium, but not in a platinum cell. And so that sort of cued me on, because that was the difference between the two light neutrinos that one can formulate in this pattern and the 88.2 keVs, and also the minus 149 in the downport mass. So this suggested to me that perhaps there's a decay somehow and a transfer of that energy to downports. And another thing that interested me in the cold fusion studies were that there was a preference apparently for lithium in these experiments, and if you have 11 downports, there are 11 downports in the common isotope of lithium. There's 4 times 2 in the neutrons and 3 times 1 in the protons. So this basically was my theory that perhaps energized D quarks, which get that energy from decay of neutrinos, muon neutrino to the electron neutrino, and then produce a variety of observations that are called cold fusion. Another thing I did was I sort of estimated the total X-ray energy that they observed and on their films. And if you can do a rough estimate by the amount of time is 950 hours. This is sort of the solar neutrino flux that's estimated. There may be some discrepancy as to this number, but for the purposes here, I'll use it. And if you multiply it by 1 plus 11, which is the 149, and 11 times 149 times that mass, you get that number, and then you convert that and divide by the 3 types of neutrinos, you get that value, 12.7 kilojoules per centimeter squared, and they observed a total of 12 plus or minus 0.4 kilojoules per what area of their palladium, I'm not sure. But basically, that sort of suggested to me a role for those things in cold fusion based on the X-rays. And the actual mechanism of why this would occur, based on my reading, was that this neutrino decay would be perhaps enhanced by cavity quantum electrodynamics. This quote basically sums up when the size of a cavity surrounding an excited atom, it's normally used for looking at atoms, but it has also been proposed in 1992 for looking at neutrinos, but not at X-ray levels, looking at like radio frequencies, microwave frequencies. Here we have the cavity surrounding an exciting atom is increased to the point where it matches the wavelength of the photon that the atom would naturally emit. The vacuum field fluctuations at that wavelength flood the cavity and become stronger than they would be in free space. This state of affairs encourages emission. The lifetime of the excited state becomes much shorter than it would naturally be. So here you have neutrinos, in my opinion, as I see it, from the sun predominantly, which is the source of the neutrinos, that have changed into the heavier versions, flowing through these systems, these cold fusion systems, and then at certain appropriate distances between particles in those plasma-like states, you have a downport sucking up that energy from the neutrino and converting it into an electron neutrino, and then you have the X-rays. And also in lithium, the same sort of thing with the 11 quarks. And there's a couple of numbers here that was kind of relevant because the average separation between deuterons and heavily loaded palladium is about 1.4 times 10 to the minus 10 meters, which is 10 times the wavelength of that 88.2 kilo electron volts. So there's basically an integer multiple of those resonance wavelengths. And in summary, and concluding, elementary particle charges can be described in an elegant and economical way using this 5 times 8 times and 6 groups approach. Its neutrino and downport mass calculations and cold fusion X-rays quantitatively suggest a role for neutrino and perhaps muon neutrino and tau neutrino decays into electron neutrinos with the rest energy transferred to these down quarks, and this transfer is hypothesized to be enhanced in cold fusion systems through cavity quantum electrodynamics. Also, I wanted to add that I didn't add in my previous preview was the predominance of neutrinos from the sun suggests maximizing non-overlapping regions of palladium or nickel, whatever metal you're using, surface areas. So you're maximizing that area and facing the sun, which would be like almost like a solar panel. So these would all basically not only be solar sort of neutrino detectors, but enhancers if you can get it to exceed the excess heat capabilities. And also, there's the ability of linear accelerators like the one at Los Alamos to produce copious amounts of muon neutrinos and antineutrinos. And that makes a definitive test of this theory possible and potentially harnessable. You just basically have, hopefully, a mobile cold fusion system. You have control and palladium sample, whatever, in outside the beam, and you have both inside this beam of heavier neutrinos, and you can almost instantaneously, stand back, find out if there's producing these anomalies. And also that would suggest a collaboration between various fields, cold fusion, solar energy, neutrino, and cavity QED industries should be encouraged. One other thing I forgot to mention was that the X-ray energies of a lithium that has all 11 down quark decided might also be in the gamma ray region, so it's something people might want to look out for if it's all released at once. So that's about it, and thank you for your attention.
Very exciting. Let's look at the discussion. Dr. Morrison, I think is first.
I was interested in your estimation of neutrinos, where you see the electron neutrino is 0 mass, the muon is 149, and the tau is 11 times that. Now, firstly, if any of the neutrinos have mass, they must all have mass. So it's very surprising you can make 0 mass for one.
Why would they have all that mass?
It's a question of the eigenstatement of neutrino oscillations. Now you can say you abandon neutrino oscillations, but under conventional theory, you should not have any 0 mass. The second point is that the muon neutrino is 149, and the mass of the electron is 863, 6 times as much. Therefore, the mass of the muon neutrino should be 1/6 of the electron neutrino, which is 80,000 electron volts. Now, in the theory of the Big Bang, we have lots of neutrinos flying around, and every cubic centimeter contains more than 100 neutrinos of each of the 3 flavors. So if you give each of these, I mean, it's a tremendous number. If you give each of these 80,000 electron volts, then it's inconsistent that the mass of the universe will be far too high. I mean, you can't have a mass of neutrino more than about 10 or 20 electron volts. So to have 80,000 is impossible. Similarly, the tau neutrino is in the excluded region. You cannot have neutrinos in that mass range.
I recognize that the mass that I get for neutrinos are much higher than people have estimated. But if you look at the particle data review of particle physics, properties of particles, there are ranges that it falls under. I mean,
No, sorry, that's an entirely different thing. This is an experiment which measures an upper limit of the mass of the muon neutrino. You get this from quantum decay. What I'm talking about is something different, which is in astrophysics. You take the Big Bang theory, and there's a certain amount of evidence for that. Then there's a region which you cannot possibly have neutrino mass, and both your mu and tau neutrinos are in this mass range, which is impossible.
Well, I can only say that perhaps maybe there's a decays of those neutrinos early on, and therefore they're not.
We have a presentation from Professor Kasagi. The presentation is called Anomalously Enhanced Deuterium DP Tritium Reaction in palladium oxide observed at very low bombarding energies.
Well, first of all, I thank you to the local organizing committee to present this wonderful contest in this conference, and I was very surprised to get the first prize. And maybe, I also thank to the people who maybe they urge to me to make more practice hardly to speak English very smooth. So I already, this morning, Peter Hagestein and King, both two people referred my experiment, and the King's comment, the audience might be confused, and so I just brought one spectra here. What I thought, that Peter talked to this spectra in this region up to let's say 17 MeV or more. We observe the proton event. That's the Peter's comment, and then Kim's comment is just this sharp peak. This is an ordinary D plus D reaction makes a proton, and this proton. And what I'm going to talk here is this yield of this proton down to, let's say, 2 keV. So I want to save my time. But I want to see is I'm just put a question here. Is the DD reaction in metal really enhanced or not? And if yes, in what kind of metal the DD reaction can be enhanced? And also, how much quantity the enhancement is. And to that purpose, we designed the so-called low-energy, high-intensity beam generator at our laboratory. Our laboratory is the Laboratory of Nuclear Science at Tohoku University. And in this machine, we can get a beam, let's say, from 1 keV to 100 keV. And quality of beam we require, or we are now obtaining, is something like this. The beam spot of the beam size is something like a 3 millimeter phi diameter. And we can get a beam, very high current beam in our sense. For example, at the energy something around 6 keV, we can get a beam current up to, let's say, 0.5 milliamps. And for example, the 2 keV, we can get beam current, let's say, 0.2 milliamps to 0.4 milliamps. And the technique we can get such a high current is just in order to extrapolate the beam extract the beam from the ion source, we need a very high potential, extracting potential. Let's say in this case we have 25 kilovolt. And using this magnet, we separate the atomic beams and the molecular beams, and then transport to this station. Here, we decelerate the beam energy. We put a deceleration electrode here. So in this sense, we can decelerate the beam from 25, let's say 25 keV, then apply the potential 24 keV, then you can get 1 keV beam over here. But during the transportation, the beam might be neutralized. So we put the magnet just before the target. That's the way we did. And inside the chamber, of course, the neutral beam go through straightly, and this has a very high energy, something around 25 keV. So we don't worry about this beam, and only the low energy beam was bent to the target. Here, in this case, we cooled down the target by using the liquid nitrogen. And the temperature, we estimate the temperature at this point, the bombarding spot, something around minus 160 in centigrade. And we also use our silicon telescopes, delta E counter system just to make sure the proton event, there is only proton event. So our target conditions were something like this. This titanium and ytterbium was the, for the data which I reported the last conference. But in this case, in this time, we didn't have a cooling system, so we didn't cool it. And deuteron inside the target is realized by the various method. For the titanium case, just gas loaded. And for the ytterbium and the palladium case, we didn't do anything. Just wait for the, because we are impinging by deuteron, so just wait for the deuteron, enough deuterons accumulated inside the target, inside the metal. And then for this stuff, this is a palladium oxide, palladium gold, brought one of my colleagues from Russia, Dr. Lipson brought us, and in this case we did the electrolysis to charge, to load the deuteron. And those targets were cooled down to minus 160 degrees. And for this target, we bombarded this side, the palladium oxide side, so beam is coming this way, and the thickness of this palladium oxide layer is something about 50 nanometer. And I just showed it. This is the this is really only the proton events we are measuring, and the noises, electric noises, are just like, this is just two-dimensional plot for the delta E versus E spectrum, and so this is just one line, and this energy is exactly the expected energy from the kinematical calculation. So what we observe, what we measure, is so-called peak target yield. And we have a deuteron. So assume this blue dot is just a deuteron inside the metal, and we are impinging the deuteron from the outside. And when the deuteron get into the metal, then it slows down. So we have to know this ability, slowing down probability. And also we have to know the number of the target deuterons. That's one of the difficult things we have to know. So right now, we just are assuming this way. For the thick target yields, therefore the yield integrated from zero energy to the bombarding energy. And then we need this quantity, the stopping power of the deuteron for the various material. And then we need a deuteron density over here. So what we analyze right now is the number of the target deuterons is just assumed to be uniformly distributed. And to see how much the reaction cross-section or reaction rate is changing, we need a standard cross-section for this low energies. And we use the D plus D reaction cross-sections, which is parameterized by Bosch and Hale. And this cross-section did not include the edge enhancement effect. So this is just corresponding to the cross-section of bare deuteron and bare deuteron DD reaction. And for the stopping power, we use the also parameterization by Anderson-Ziegler for this region. And to make sure the target, the is not so much jumping around. We measure the yield, proton yield at 10 keV very frequently, each run, before and after. Not only before and after. You see, this is one of the examples we did an experiment in such a way. So we measure the 10 K, we measure the proton at 10 keV, and then we switch to the 5 keV. We can get the proton yield something like here, and then after that we switch to the 10 keV again. Then we know the during 5 keV, in the average sense, during 5 keV measurement, we have this kind of number of the deuterons. And even if we have no yield, we should do it. In this case, we bombarded the 4 keV for example, for 2 hours. Then after 2 hours, we switch to the 10 keV again. Then we got this one. So if you look at, for example, 5 keV data, so this trend of the yield is just to follow the yields of 10 keV. So in that sense, and then after that, we always normalize to the 10 keV. So in that sense, what we measure is just a normalized fixed target yield, not absolute. Okay. So since I don't have so much time, I just go to the result. So this is the result which I already reported last conference for the Deuterium and titanium case. The green is Deuterium and the blue one is the titanium. And you see, as I said, these yields are normalized at 10 keV. And you see the very quick decrease of yield as a function of as lowering the neutron energy. And this is the dotted line shows just a standard predictive yield. That means without any enhancement. Well, actually, these two data sets just follow this line, though I said that there is a little enhancement. For example, the for Deuterium case, if we parameterize this enhancement as a screening potential, we got this value for Deuterium and the titanium, 20 MeV for titanium. But for the palladium and the palladium oxide case, we have a very big enhancement. And here, you see the blue line, I show again the standard predicted value. That means without no enhancement. If the cross-section follow the bare DD nuclear cross-section, the fixed target yield should be follow this line. But for example, you look at the palladium data, which is indicated by the orange color here. So the enhancement started something around 6.5 kV. Then we got something around this value here. And if you see the palladium oxide data, the enhancement already started much higher energy, maybe 9 kV or 8.5 kV. And down, we got the data down to 2.5 kV. Here, the enhancement is something like 50 times. And if we parameterize same way as we did for the titanium and the Deuterium, we got a screening potential of 600 MeV for the palladium oxide and 250 MeV for the palladium. Since the chairman is now standing up, I have to stop here. So I guess I just put the one slide over here. So if the cross-section can be extrapolated with this string potential parameterization, that means we already have this amount, even if zero energy. Then at the room temperature, or let's say relative kinetic energy of a deuteron is something around 0.025 electron volt, then the cross-section is something like this orders, 10 to minus 40 square centimeter. And for the palladium case, it is this one. And then if we apply this one to the thermal nuclear reactions, we get one nuclear reaction per cubic centimeter per second. If you have a deuteron density of 10 to the 18 plus cubic centimeter for palladium oxide case. So I have to stop here, but I just want one slide over there. So then the problem, can we extrapolate the question for the future? Can we really extrapolate the cross-section in this way? I mean, this parameterization is useful down to, let's say, electron volt region. So in that case, in this sense, we really need the data at much lower energy, of course, again. And then the next question is stopping power. Actually, no stopping power data below 10 keV per nucleon. So we should develop the methods to measure it. And we are thinking several ways. One of them is we might to measure the M-shell electron ionization cross-section and so on. And also we need the target deuteron density. Of course, there is not so much fluctuation, but there is a fluctuation. So we have to develop the technique to know the target density during the bombardment. To do that, we are planning to measure the depth profile of deuterons by so-called elastic recoil detection at various energies. Thank you very much.
We have time for just a couple questions. Dr. Martin.
I think it was very appropriate that this gets the first prize, but it's certainly very well carried out and very carefully done experiment. And those similar ones are very good. On the other hand, I think when we discussed this last night, there are some points. In a perfect world, you use a thin target so you know exactly the energy. But in a real world, you simply don't have enough events, and the cross-section is so very, very low that you couldn't possibly use a thin target. So you have to use a thick target when you're adding up very things. Now, when you're doing that, there are worries, and I think you've pointed them out, that you don't know the stopping power, and if you don't know the energy of the particles actually interacting, you make a mistake. So what I would be happy if you were to assume other stopping power dependencies and see how much that changed your results.
Yeah.
Now, you also used a screening factor, and last time you said it was about 80 electron volts. Now you say 600. So I went to CERN and talked to the top people of this there and said, is this a reasonable value 80? And said, no, it's far too high.
Yeah, because for example, there is such kind of calculation by each model in the titanium case. He said, from his calculation, we got about 50 electrons in titanium case. Yeah, that's right. 80 electrons.
I'd just like to warn people that in addition to the statistical errors shown, there are systematic errors for unknown quantities. Now, the other thing is, of course, some people might think that maybe, we keep on talking that the barrier means that the fusion by DD fusion is wrong by a factor of 10 to the 40 or something. And I think people should realize this has not changed. Going from 6 keV to 2 keV is a factor of 3. You fall a factor of 4 orders of magnitude. So when you go from 2,000 electron volts down to 700, another factor of 3, you fall another 3 orders. And then you go from 700 down to 230, you fall that. And you fall. So to get down to the very low energies, and you're 0, you're still going to be down 10 to 30, 10 to the 40. So there's still this barrier penetration that cold fusion cannot work by this enormous factor.
But anyway, it is important to see real cross-section in real low energy, because this is completely not explored region for the nuclear physics also.
Okay, thank you very much. Our next talk will be by Dr. Mastromatteo on nickel submicron thick layers heated over Curie temperature show high temperature spots if exposed to hydrogen atmosphere.
Thank you for giving me the possibility to explain better the content of my work. I repeat again the title of the poster. And I'm working in a microelectronics company, as I told you the previous time. So I did the work just to show how the technology can help to build some special cell that can put in evidence better what can be used to enhance the yield of this kind of phenomena. The work was just preliminary because the aim of the work was just to study the behavior of the electrical resistance of a thin film of nickel, nothing more. For doing that, I would like to use special solid films with high content of hydrogen that are commonly used in the microelectronics industry. Also the behavior of that layers is well known. This is the layout of the cell. I showed in my previous presentation the dimension, the real dimension of the cell is very small, as you can see. Very small cell. Here you can see the snake that is the nickel layer, is the white one. The brown one is just the heater, just below the hydrogen content layer. I will show in a microsection the structure of the cell. Okay, just to have an idea of the dimension that I used, I had on the top a nickel layer of 0.1 micron thickness. The yellow-green layer is a hydrogen-rich silicon nitride deposed at 350 degrees centigrade. In that condition, enhancing the chemical reaction with the plasma, you can have a lot of unsaturated, unreacted bonds. So you have a big amount of silicon H bonds and nitrogen H bonds. Okay, the field is well known, so you can have in the literature all the characteristics of this kind of layers, nothing special. The thickness of this layer was 2 microns. And here we have the heater, is a polysilicon built layer. The thickness of this layer is 0.5 microns. And below we have a silicon dioxide, just to separate electrically the heater from the substrate that is a standard silicon substrate used in microelectronics. Here we have the electrical configuration of the cell, nothing special. The heater was biased by an external power supply, and the nickel electrical resistance was monitored by a standard multimeter. And but you can see here that you can bias that cell in many ways. So you can put some electric field inside this layer just to push hydrogen into the nickel. I used in my experiments sometimes this configuration. And also you can bias the nickel resistance and also use that resistance as heater too. As I told before, this layer was deposited at 350. So going up, respect that temperature, you can have a release of hydrogen from that layer. Also, this fact is well known in literature, and the activation energy of this mechanism is a little bit below 1 electron volt. To do that in a better way, I used this kind of chamber as an iron steel chamber with a 1 liter volume. Some connections just to be able to fill the chamber with gas, just in case to confer hydrogen absorption, also using gaseous source. And okay. This is the open chamber. You can see the sample in place. This is a better view of the sample with the electrical connections. Here we have high vacuum electrical pass-through connection just to have the capability to connect by all the instrumentation. And first of all, it is important to know the temperature of the sample. So, monitoring the behavior of the electrical resistance of the nickel film, you can clearly see